June 1742, Kaliningrad, Russia. This is Christian Goldbach, a math professor, working on number theory in his room. Just a few days ago, he stumbled upon a problem concerning prime numbers and has been trying desperately to solve it. Hours turned into days, but there was still no solution. Now, it was time to reach out to his close friend, the mathematician giant, Euler. For some time, they had exchanged letters. Whenever Goldbach couldn't solve a tough problem, whether it was about perfect numbers or Fermat's numbers, he would send it to Euler for help. And Euler always responded with solutions, but not this time. When Euler received Goldbach's letter, he read it and thought to himself, "Can every number be the sum of two prime numbers?" He thought it was pretty simple that he didn't spend much time on it. Instead, he reformulated it into a simpler version and sent it back to Goldbach. Little did he know that this simple idea would later be called Goldbach's Conjecture, one of the toughest unsolved problems in the history of mathematics. It's so straightforward, yet for 283 years, no one has been able to prove or disprove it.
Hold tighty.
This conjecture is such a dangerous problem in math that most mathematicians have warned against wasting time on it. Here's how it works. Goldbach initially proposed in his first letter to Euler that every whole number greater than 5 could be written as the sum of three prime numbers. A prime is a whole number that is only divisible by 1 and itself. For example, take 6. 6 equals 2 plus 2 plus 2. For 29 equals 11 plus 7 plus 11. Then, Euler simplified it. Every even whole number greater than 2 can be written as the sum of two primes. For example, 6 equals 3 plus 3. 8 equals 3 plus 5. He claimed that if this is true, then Goldbach's original idea, that every odd whole number greater than 5 can be written as the sum of three primes, must also be true. This follows because if 2n equals p plus q, where p and q are primes known as a Goldbach partition, adding 1 to both sides of the equation results in 2n plus 1, an odd number, and p plus q plus 1, which is the sum of three prime numbers. At the time, the number 1 was considered a prime. However, it turns out both forms are harder to prove than expected. Euler's simplified form is now known as the strong Goldbach conjecture, and the original form is known as the weak Goldbach conjecture. Let's picture a simple graph. Two lines coming out from a single point, each representing a set of primes starting from 2 and going off to infinity. Now, if you draw lines from each of these numbers, making them parallel to another line, and do the same for another set of lines, then their intersections give you sums of two primes. These intersections correspond to even numbers, like 2 plus 2 equals 4, 2 plus 3 equals 5, and so on. As you keep going, you'll notice something interesting. Larger even numbers have more and more ways to be written as the sum of two primes, ignoring repeated pairs. This shows that as numbers get bigger, there are way more combinations, or partitions, for writing an even number this way. Using the Hardy-Littlewood asymptotic formula, we can estimate how many ways an even number 2n can be expressed as the sum of two primes. It's roughly n divided by the square of the natural logarithm of n. For big numbers, this becomes a huge count, meaning there are tons of ways to break down a large even number into two primes. So that means the conjecture holds true for now. But hold on. Here is the number of Goldbach partitions, or prime sums, for even numbers up to 50 that I calculated. And now, when you plot these counts on a graph, it forms a beautiful shape resembling a comet. On the vertical axis, you have the number of partitions, or the number of prime sums, and on the horizontal axis, you have the infinite sequence of even numbers. This pattern is called the Goldbach comet. Now, here's the tricky part. Even though primes are more frequent among smaller numbers, as numbers grow larger, primes become rarer. The comet starts off very dense and gradually becomes less dense as you move along. There could be some very large number that has only one or two ways of being written as the sum of two primes, or maybe none at all. Who knows? It could turn out that the conjecture is false, with some sufficiently large even number having no prime sum. When you draw lines from each even number on the x-axis to its corresponding red dot, you'll notice that these lines fluctuate randomly. Sometimes the partition count goes up, sometimes down. This irregular behavior reflects the fact that as even numbers grow, their number of representations as a sum of two primes does not increase in a smooth, regular manner. Instead, the fluctuations occur because the prime numbers themselves are distributed in a seemingly random way among the integers. By extending each line into a rectangular bar, you create a stacked bar chart, often referred to as Goldbach levels, or PO3, power of 3 levels, in trading. In 3D representation, these bars can be colored differently, with each color representing a distinct prime number. In this visualization, each row corresponds to an even number. The height of each bar indicates the one of prime numbers, and the number of bars in each row equals the number of partitions for that specific even number. The point is that as prime numbers get rarer as numbers grow, and the chances of occurring one large enough even number having a couple of prime sums, or at least one prime sums, make it look like the conjecture could be wrong with no prime sum. But thus far, no such large number that does not obey the same rule has been found. And it's not for lack of trying. Mathematicians have tested every single number by brute force. Back in 1938, Niels Pipping showed that the Goldbach conjecture works for every even number up to 100,000. Since then, computers have pushed this limit way further. The latest check confirms the conjecture holds for even numbers up to 4 quintillion. That's a 4 followed by 18 zeros. Impressive as that sounds, it's not enough for mathematicians. Verifying individual cases, no matter how large, only covers a finite range. To truly settle the conjecture, they need a universal proof that works for all even numbers, no matter how massive they get. Faber and Faber, a British publishing house, announced a $1 million prize for anyone who could provide a complete proof of Goldbach's conjecture between March 20th, 2000 and March 20th, 2002. Despite this enticing offer, no one was able to claim the prize, as the conjecture remains unproven to this day. In 1939, Soviet mathematician Lev Schnirelman proved that any even number can be expressed as the sum of no more than 300,000 prime numbers. While this result is mathematically correct, it is far from proving Goldbach's conjecture. In 1937, Ivan Vinogradov proved that every sufficiently large odd number can be expressed as the sum of 3 prime numbers, making a significant contribution to the weak form of Goldbach's conjecture. However, his definition of sufficiently large was astronomically high. Initially, n greater than or equal to 3 to the power of 3 to the power of 15, which is approximately e to the power of e to the power of 16.573, a number with over 6 million digits. Later, Chen Jinggrun and Wang Yuan refined this bound to e to the power of e to the power of 11.503. Still an immense number, but far more manageable in comparison. Finally, more than 250 years after Goldbach's original statement, Harold Helfgott completely proved the weak Goldbach conjecture in 2013. His proof showed that every odd number greater than 7 can indeed be expressed as the sum of 3 primes. This marked a major milestone, but left the strong Goldbach conjecture unproven. So why are primes so hard to understand? Basically, it's because we don't really get the sequence of prime numbers all that well. They behave much more randomly compared to other sequences. Take the sequence of square numbers: 1, 4, 9, 16, 25, and so on. I can easily tell you what the 1000th number in this sequence is, but I can't do the same for primes. I have no idea what the 1000th or any nth prime is. We just don't have a good formula for that. There's this famous quote from Paul Erdos, one of the greatest mathematicians of the 20th century. He was chatting with Einstein and some colleagues at the Copenhagen School in the 1920s, and one of them, Werner Heisenberg, shared their interpretation of quantum mechanics. Einstein didn't buy it because it seemed to suggest that the universe had randomness in it. He famously said, "God doesn't play dice with the universe." Erdos, kind of riffing on that, said, Maybe God's not playing dice with the universe, but something fun is definitely going on with prime numbers. In fact, Goldbach's conjecture is so famous that people have written novels about it. One of them is Uncle Petros and Goldbach's Conjecture. The story follows Petros, a Greek math prodigy obsessed with proving the conjecture. He gets closer and closer to solving it, but eventually goes mad in the process. The idea of the novel is that the reason Goldbach's conjecture hasn't been proven is that it drives anyone who gets too close completely insane. If you told a mathematician you're working on Goldbach's conjecture, they'd probably think you're nuts. Nobody has any real idea how to tackle it. The question is simple. Is there some huge even number that can't be written as the sum of two primes? If just one such number exists, the conjecture is disproved. But why is this so hard to tell? Maybe that's why Terence Tao, one of the greatest living mathematicians, once said,
some problems sometimes the tools are not there. It doesn't matter how smart or quick you are. The analogy I have is like climbing. If you want to climb a cliff that's 10 meters high, you can probably do it with the right tools and equipment. But if it's just a sheer cliff face, a mile high, and there's just no handholds whatsoever, just forget it. It doesn't matter how strong you are or whatever. You have to wait until there's some sort of breakthrough, like some opening occurs like halfway through, up the cliff, and now you have some easier sub-goal. There are some speculation as to some possible ways to attack the conjecture, but nothing is really promising currently.